precipitation reactions. And precipitation reactions basically happen when we put two liquids together and get a solid. Right? So we did one of those, right? We did that. We did a precipitation reaction. We put two liquids together and we get a solid. And so what happens in a precipitation reaction? Most of the time they're double displacement, which means our cations and our anions switch places, right? And it's basically when they ionize and then only one solid forms, right? When they switch places, one of those new compounds is soluble. And so if one of the new compounds is soluble, then it's still ionized. But if one of the new compounds is not soluble, that forms a solid, right? That's what really happens. So when ionic compounds dissolve in water, the resulting solution contains separated ions. We put things in water, they separate. If there is something that forms that is not soluble, that's the precipitant. Okay? And it doesn't happen in every reaction. Sometimes we'll put two soluble things together and nothing happens because everything in that reaction is soluble. And so it's not going to form anything new because let's say it did form something new, it would immediately dissolve again. Right? Does that kind of make sense? That's what's called a no reaction, right? We'll see some of these in this examples. But precipitation reactions, basically we put two things together, they ionize, and then something forms that is not soluble. So this is what an example of this looks like. We have a reaction of potassium chromate and barium nitrate. This is what they form, potassium nitrate and barium chromate. The reaction on the left, or A, is before the reaction occurred. All of them exist as ions since they're ionic molecules. So barium is separate from nitrate, potassium is separate from chromate, right? They've all dissolved. After the reaction has occurred, BaCrO4, or barium chromate, is not soluble. And so you see at the bottom here, we've got this clump of barium chromate molecules, right? That's the solid that has formed and settled to the bottom. And the potassium nitrate are still floating around ionized at the top. And so this is the real picture of what that looks like. And so now I hope you're wondering, well, how do we know what dissolves and what doesn't? Ding, ding, ding. Okay, next slide on your handout is going to be rules that we use a lot. Do you want a copy of that that's bigger, like more accessible, or is that going to be fine? Okay, so this is a sheet that you'll get. Oh, not the next slide. Maybe 2 slides. There we go. Okay, this is a sheet that I'll give you on tests. So these are not rules that you have to memorize, but there's just a lot of things here, right? These are rules for solubility. And there's some exceptions, but for the most part, I give you the rules, right? I don't need you to memorize every single exception. If there are big exceptions, we put them on here. But for the most part, these follow the rules. So that means most nitrate salts are soluble. When we say salt, that's just an ionic formula bound with either a group 1 or group 2 cation, right? A salt is almost any ionic formula formed from a group 1 or group 2 cation. So most things that are bonded with nitrate are soluble. Most group 1 salts except NH4 are soluble. So most things that are in group 1, lithium, potassium, almost anything that it's bonded with is soluble. Okay? Most chloride, bromide, and iodide salts are soluble, except if they're bonded with silver or lead or mercury. Do you see how the exceptions work? So if I had, for example, this formula, AgCl, would it be soluble or not?
No.
No, because we said, yeah, most chlorides are soluble, but this is the exception. It's bonded with silver. Okay, so you have to know how to be able to read your solubility rules here. Okay, most sulfates are soluble except if it's bonded with barium, lead, mercury, thank you, and calcium. Most hydroxides are only slightly soluble. So these are ones that I wouldn't necessarily call soluble. These are 2 that are for sure. NaOH and KOH are soluble. And these 2 they call are marginally soluble, which basically means not so much.
Wait.
Okay?
Soluble.
Soluble means it's able to dissolve. Okay? Able to dissolve. Okay, so if we would see something that's like this, if we have, I don't know, if you see NaOH, AQ, right? AQ means it's been dissolved in water. right? And if something is not soluble, we would write it like this, AgCl with a solid, right? Because it's not soluble, it's not dissolved in water, it's a solid right now. So this is where our states of matter in our chemical equations are super, super important. Right? Before then I said it's not that important if you keep the L or G or S or whatever. Well, now it is. Okay, so if it's dissolved and if it's soluble, we put the AQ, and if it's not soluble, we put the S for solid. Okay, most of these are only slightly soluble except for those containing the cations in Rule 2. So this is a sheet you maybe highlight, put a circle around something. You'll need to be able to refer to these rules quickly and often, so I want to make sure you know in your notes where those are at. All right, so now we're going to look at a couple examples. Which of these following ions that form with lead are going to be soluble in water? Okay, of these compounds, let's say they all are going to bond with lead. Which of them are soluble? Take a look over that and see if you can come up with any of them that are soluble. I have to get my rules out. So S or PBS, would it be soluble?
No.
PBS, would it be soluble, yes or no?
Public broadcast station.
What do we think? Soluble? Slightly. Okay, for the most part, we're going to say if it's only slightly or marginally soluble, we're probably really going to call that a no. Okay, so really I would say probably that one's not soluble. Is PbCl2, yes or no?
No.
Not soluble. Okay, because that's one of the exceptions. PB,
Wait, why isn't it soluble?
this one is because of rule number 3.
But it says it is.
Most Cl salts are soluble except Ag, Pb, and Hg. Okay, is lead nitrate soluble? Yes. Because it says most nitrates are. Is lead sulfate soluble?
No.
Most sulfates are soluble except...
Oh, no.
No. So this is rule number 4. Is Na
Yes.
to Pb soluble? Yes. Right? Because it's a group 1A. Sodium is in group 1. So it says most are soluble. Yeah. Okay? So you're going to have to be able to identify which one are and which one aren't. So now we're going to look at how do we write these equations out, knowing which ones are soluble and which ones aren't. And so we're going to look at a couple different ways to write out chemical equations. What we've written so far is called the formula equation. Okay? It gives the overall reaction stoichiometry, but doesn't give very much specifics about the individual ions. So what we're used to writing is called the formula equation. Okay? We usually show our reactants and our products as full compounds, regardless of if they're dissolved or if they're not. This is what we are used to, the formula equation. Okay? But we're going to move into something called the complete ionic equation. The complete ionic equation tells us what happens if everything is dissolved and ionized. So this is when we write the equation showing everything that has ionized, they're represented with their charge, and with their subscript as a coefficient. Okay? So in that last example, you guys can see the first example that we gave. Okay? The very first formula that we said was Ag, or the formula equation, AgNO3 plus NaCl yields AgCl plus.
It's not that because they're all moving around together.
Right, so it says that this one was aqueous, this one was aqueous, this one was solid, this one was aqueous. Okay? So when we write the complete ionic equation, we're going to say, well, these three substances, 1, 2, 3, are really not full substances. They're ions in that water because they're dissolved. And so we split them up. Ag minus 1 plus NO3. No, Ag is plus. Minus 1 plus Na plus Cl minus. We know that AgCl is a solid, so it gets to keep this. And then we write sodium and...
So AgCl would be the solid on the bottom
Right.
of the water.
Right. Okay, this is the exact formula in the exact lab that we did. Right, our limiting reactant lab was this exact, formula equation. Okay. So now we've got the formula equation, we've got what's called the complete ionic equation, and what we're really working toward is something called the net ionic equation. What does net usually mean?
Total.
It's kind of total.
Altogether.
Yeah, okay, yeah, that's fine. Net means basically, I guess total is as good a definition as any, but the sum total, right? The pluses, minus, negatives, or whatever you want to describe it as, right? So the net ionic equation only is going to show those components that are undergoing a change. Okay, it's only going to show the things that are actually changing. And so let's look at our complete ionic formula again and see what happens to get to our net ionic formula. Okay, our complete ionic formula was this. Okay, which is our solid here? AgCl. And which of our reactants helps us get to our solid? Right? Don't silver and chloride have to help us get to our solid? Yeah. And so when I'm looking at my net ionic equation, I'm saying what's different in a different form on the left than on the right? Well, silver goes from aqueous to in a solid. Chlorine goes from aqueous to in a solid. Sodium goes from aqueous to aqueous, so does it change? And nitrate goes from aqueous to aqueous, so does it change? No. Okay, so when we write our net ionic equation, I'm going to write it down here below. Net ionic equation.
Seems pretty self-explanatory.
It is pretty self-explanatory. We would say Ag plus, and you have to write an aqueous here, plus Cl minus aqueous yields AgCl solid, right? That's my net ionic equation. That's it. And then the things that are not interacting, sodium and nitrate, these have a special name called, you looked ahead. Spectator ions. Okay, spectator ions are the things that don't do anything. They just watched it happen, right? Silver and chlorine combine together to form silver chloride. That's our complete ionic and net ionic equation, sorry. And then those two are called spectator ions. Okay. They don't participate in the reaction. So we are going to write out these things. I think I left it blank on your notes, right? Okay, so we're going to build this one from the beginning. You have to build and balance the reaction between cobalt chloride and sodium hydroxide. We're going to write the formula equation, then the complete, then the net.
You already gave us the formula.
I already gave you the formula. Okay. Did I give myself the formula? Okay, I did. All right. What about, did I give myself the complete ionic equation? No, I didn't. Okay. So if I'm going to look at the complete ionic equation, I should have let you form which one was going to be the solid, right? I want you to be able to identify which of those two results or those two products would have been our precipitate. Could you have done that by yourself? Looking at our solubility rules, could you have looked at cobalt hydroxide and said most hydroxide are only slightly soluble, so that means a no.
Yeah.
So cobalt hydroxide would not have been soluble because we know salt is, right?
Wait. So cobalt hydroxide is the
Hold
thing
on.
If the sodium and the chlorine are just spectating, why do you need those compounds? Why can't you just put cobalt and hydroxide in there?
You still need it for the first part of the reaction. Are you saying just to form cobalt hydroxide in general? Right. It just might be that you don't have that. You don't have plain cobalt and you don't have plain hydroxide. But sodium hydroxide is really easy to find. You know what I'm saying? It's not, ions don't exist by themselves. So I can't go get a bottle of OH minus 1 out of the cabinet.
Yeah.
Right? I have to have it in an ion and then let it do its work itself.
So if you did have that and cobalt, you put it in water.
Yes, you could. But those things just don't exist on their own. So that's why. All right, what was your question?
So the thing that is forming is the cobalt hydroxide.
Right, that's going to be what falls out of the reaction. That's going to be the solid. So if I'm writing my complete ionic equation, what's cobalt's charge here? Cobalt plus 2, and it's going to be aqueous, right? Plus, what's chloride's charge? -1. And how many chlorides do I have? This is super important. You're going to forget to do this. If there's 2 chlorides, you need to represent 2 chlorides in my complete ionic formula. My complete ionic equation, I'm sorry. Okay? And this is also aqueous. Okay, my next one is sodium, Na plus, and how many of those do I have? 2. This is aqueous plus 2OH minus aqueous. Agreed? Okay, now on the product side, we already determined that cobalt hydroxide is going to be a solid. Okay, so I don't have to break that up into ions, but my last one would be Na plus, and we said there's 2 of them, plus 2Cl minus, and these are both aqueous. Sorry, I know my handwriting is getting a little sloppy here. Okay, so now we need to double check on both sides. If it's helpful for you, you can just cross the things out. Right, I have 2 chlorines here, 2 chlorines here, 2 sodium here, 2 sodium here. Okay, over here I don't have 2 hydroxides because now it's in a new form. So I can't cancel that out. So that helps me take out my spectator ions and figure out what really formed, what goes into my net ionic equation, and it's got to be what's left over. CO plus 2, aqueous plus 2OH minus aqueous yields COOH2 solid. And so you double check, okay, I'm supposed to have 2 hydroxides. Do I have 2 hydroxides over here? Yeah, right? I have 1 cobalt, 1 cobalt. What happens if you build your formula equation and nothing comes out as a solid? What if all 4 of my compounds are soluble?
Those are just floating around.
Right, we just say that's a no reaction. Right, there's nothing that happens because we put them together. Even if they do form, they're going to redissolve. So there's nothing that's happening. There's nothing that's taking place. So you'll have questions in your book that are like that. It'll ask you to build the formula, and then there's nothing that happens. There's no solid that forms. So we just say it's a no reaction.
There's no net reactions.
No net. Yeah, there's no net. No. Right. Okay, let's see here. All right, we're going to stop right